In this video, we're going to look at the second type of forces called contact forces. You need to touch in order for the force to appear. The first force appears when two surfaces are in contact. What force would that call? We call it normal contact force. And we use the symbol N. Why normal? What does it mean? Well, you see, when you have, let's say, an object placed on a table, the table will push the object at an angle perpendicular to the surface. So if I rub off the table and I just draw the forces on this box, this is going to be perpendicular and this is our normal contact force. So let's add the word forces between two surfaces in contact that are perpendicular to the contact surface. You might be saying, Miss, well, what about the table? Isn't there a force on the table? Yes, there is. If I draw just the table, the book will push the table downwards, and this is the normal contact force also by the book or box. The one pointing upwards is the normal contact force by the table. These two are what we call Newton's third law pair, equal magnitude, opposite direction. Sounds familiar, right, from dynamics? If you're wondering, actually, where does this normal contact force come? Well, actually, let's look at this book of chemistry and physics stacked together. Have you ever wondered why when you stack two books, they don't fall through each other and just morph into each other? Well, you see, chemistry is made out of paper and has all these molecules inside it. Same goes for physics. And these molecules, you cannot just simply smash them together, okay? I can try. Cannot. They will repel each other. So that's where the normal contact force comes from. It's actually molecules repelling each other. But other than normal contact force, perpendicular to the surface, that appears when two objects touch each other, there's another force that may appear if the object starts to rub together. You try rub your hands, it gets hot. Why? What's that force called? We call it frictional force. Sometimes we don't really have a fixed alphabet for this, but I like to call this small f. That steals away your motion energy. So what is the definition of that? Well, frictional force appears when forces, two surfaces are in contact, and this force is parallel to the contact surface. Parallel. The opposes, this is an important one. Friction force will always oppose the relative motion of an object due to uneven layers sliding against each other. Well, what does that mean? Let's go back to the simulation. Take a close look at the surface of this chemistry book when we zoom in into a molecular scale. It's kind of bumpy, isn't it? I mean, the physics one looks better, but it's probably, if we zoom in some more, it's not even. And all of them are doing a little bit of a jiggle as well. So when you rub them together, well, if I just leave it there, there's no friction force. But when I start rubbing the books together, oh my goodness. What's happening? Look at the temperature going up. Because there's friction. These uneven surfaces are rubbing together. And as we go, woo, friction force. And you kind of smoothen out the book. Great, fantastic. And they'll start jiggling because it's hot. That is what we call frictional force. So one common setup that you will see, let me see if I find some space to write here. All right. One common setup you'll see is the box on the table. An object is moving along the surface of a road, for example. And this is where you've seen a little bit of it in dynamics. Yes, dynamics. So you have a box on the surface, just chilling or moving along the road. Well, let's say I exert a force to pull this object to the right. So I have some force. I don't know what that is, but force. Let's say I use my hand. As this object is moving to the right, we say it has a rightward velocity and is accelerating even. Sure, it can add acceleration to the right. But because it is moving, there will be this frictional force opposing the direction of velocity. Very much like drag force that you learned about in the previous chapter. So, alright, frictional force opposes velocity, always in opposite directions. Number 2, because the box and the table is in contact, if I want to draw forces on this box, I need to add another one, which is called the normal contact force. Like that. Perpendicular to the surface. Now I can rub off this table. I don't need it anymore because I just want to look at forces on the box. Okay, so forces on the box, there you go. 3 forces on the box. There are some more unusual scenarios involving friction. We'll take a quick peek at them right now. Now we know that friction can impede motion. It causes you to slow down. But did you know that sometimes friction can do weird things to push you forward instead? Imagine you are running or walking on the road like this fella right here. which direction will be the frictional force acting on the person? How does a person move forward? Can you run if you're on smooth ice? Here's a deep dive. There's some forces happening at the point where the person's leg touched the floor. And if you want to look closely, actually, you need to stand up and try this. If you are walking, your leg is pushing the floor behind you. So, if I were to draw the friction arrows, here's one friction arrow, and this is the frictional force on the floor by the foot or by the shoe. You push the floor behind. So how do you move forward? That means the floor push you forward because of Newton's third law. So this one, ayo, too big already lah, miss. Okay, never mind. You imagine they are the same magnitude lah, okay. There's an extra bit over there. And this one, we will call the force, frictional force on you, on your foot. By who? By the floor that has friction. And this is why when you walk and when you run, you can actually move forward because the floor is pushing you forward thanks to friction. So yeah, friction can slow us down. Sometimes friction actually helps us move forward. So if you're finding this hard to brain a little bit, go do some moonwalking, go and walk on the floor. But maybe if you have an escalator that's something like this, if you look right, as the person walks forward, the floor is moving behind, correct? Friction, okay, friction. Another weird example to expand this understanding is to think of wheels. What if you have a car? How do you think of a car? Okay, so if you look at a situation, you need to learn to draw the forces on the car. We're going to look at forces on the car, yeah? So firstly, you say, Miss, the tire touched the road. Okay, sure. We definitely can draw contact forces, that's N. But there's also friction. If not, how the car move forward? The tire turn, if you're on ice, you cannot accelerate forward if it's ice and it's smooth. So we need to deep dive a little bit, separate out the road and the car, and ask ourselves, what is happening when the back tire, I mean, that's usually most cars, the back tire turns like that. The tire is pushing the road behind it. So, this is the first force. This is the frictional force on the road by the tire as the car tries to accelerate forward. Wow! So, because of Newton's third law, there is also another frictional force pushing in this direction, and this is the frictional force on the tire by the road. A rough road can push a car forward. Isn't this strange? It's just mind-blowing. Force on tire is forward when the car moves forward. Just go and think about it, alright? Spend some time. So anyway, we're going to draw that here. Frictional force, forward. And if you want to, might as well add in all the forces. You can draw in weight as well. So this will be weight of the car. So analyze the system, you got all the forces. And I forgot to draw the normal contact forces now. Okay, so when you walk on the road, why does your leg not sink into the road? Because molecule oppose molecule, something's actually pushing you up. This is our normal contact force on your foot, thanks to the floor. Also likewise, if you want to draw the forces on the road, there's also another one here. So this is normal contact force on the road or floor by your foot. And that is how to think about frictional forces. So here's 3 cases we have looked at so far. Friction that opposes motion. Contact friction, sliding a box, or known as drag force. I kind of added a few forces to our diagrams here, because on the car side, we have drag force due to the wind blowing on the car. We have also the friction force on the road, off the road, on the car wheels that actually pushes it forward. So there's lots of forces going around here. What you need to learn is how to identify these forces and which direction they're actually pointing to. So these are contact forces. There's one more very common scenario, but in order to know that, we need to know one more contact force, which is called tension force. Sometimes we call it tensile forces, compression force. Really mean the same thing. Usually we use the letter T or force with a T down at the bottom. So these force appear when you have a rope, a rod, a string, such as a pencil, that is stretched or compressed. I'm trying to break the thing. Okay, so we have seen this in hanging objects. where you have a pendulum or heavy some mass hanging there, where would you draw the tension force? Turns out it depends. Are you looking at the tension force on the object? Because if you are, then you need to draw the object separately. Who keeps the object pulling upwards? Tension force. So you draw a tension force. If you are drawing the force on the wall, no, not wall, this roof or ceiling, then who pulls the roof down? The string, because tension force. But then if you want to draw the forces on the string itself, then you need to draw this string and say, somebody's pulling me up, somebody is also pulling me down. And it turns out so many T's you can draw. But most of the time, we will only draw tension force on the object of interest. So you want to look at what's the forces acting on the object. We usually, in the future classes, I'll be drawing weight on the object and also tension force on the object. But know that tension is actually distributed along the entire string. You see this in hanging objects. You will see it in pulley systems like this one, and you will see it also, not surprisingly, in springs, because, spring is also stretching an object. So we consider Hooke's law tension force as well. So if you want to draw these forces, it really depends. If you're asking, who's pulling this heavy mass? Oh, the string. So there's a tension force in there, pulling this object to the right. That's because this thing's pretty heavy. So something is pulling this whole thing down. So that's going to be our FG or weight. So lots of places can draw tension force. It depends on what object you are studying. What acceleration do you want to find? For our our spring here, if the object is compressed, the spring is compressed, and you say, what are the forces on this mass? Tension force is actually pushing downwards. So-called tension, but more like compression force, because the spring is like, I want to push out, why you squash me? So you'll try to push out. And the object is also heavy, so that's weight equals to mg. But if you really stretch out the spring until down here, then the spring is like, bro, why you stretch me so much? Okay, I want to pull back. So you say, what's the forces on the little box? Tension force of the spring, pulling it back. We call it a restoring force. And of course, the object still has some kind of weight lah. Okay, so that's general ideas of tension force. If we put together everything though, how would it look like? Oh, well, wait, I need to write the names here. This is a compression. That's why a tension force appear. And this is a stretching or extension. That's why a tension force appear. It can work both ways. You squash something, you pull something, a tension force will appear. Okay, let's put together all these three for the last scenario that we will encounter pretty often, and that is called an inclined plane. What happens if we put a block on an inclined plane? By inclined, I mean, you look at this surface, it's flat, right? But what if I put it at an angle like this? Whoa! Will this block slide down or will this block slide up? How do we draw the forces and come up with equations for the forces to see whether will this block slide up or slide down? Now, whenever you see an inclined plane, the first thing I want you to ask yourself is, if this is a smooth surface, what force would cause this object to slide down an inclined plane? Think carefully. Who is pulling it down? Which force? Which force? Gravitational force. Weight. That's right. So there we have it. One arrow called weight. This is going to be W. Weight of this object downwards. But the object is not going to accelerate downwards. If this weight causes the object to accelerate, it's going to be down the slope. The object will roll down the slope. So what you need to do whenever you see inclined plane is you need to resolve weight, because this is at an angle theta. How to resolve weight? You decide what is going to be your axis. You see this whole thing is tilted. Tilted this way. Okay, it's tilted. So there is some components of weight that is going to be in which direction shall we choose? Let's say I don't know which one to choose. Okay, let's show this way. X is this way, tilted. Y is this way, tilted also. Your entire XY axis is tilted. They are still right angle to each other. So if we follow that tilted angle, we need to draw the components, which would be the downwards. I guess not downwards. Towards the surface. This will be, wow, what angle is this? Something sine, something cosine. Which angle to use, miss? Okay. We stay calm first, You see this theta here? How do we find the theta that is over here? Let me just tell you a shortcut. This is going to be the theta over here. Why is that the theta? Because of some geometry triangle thing. If you're curious to know more, go check out the bonus video after this on inclined plane geometry. If you cannot figure out how and convince yourself why that is really theta. Okay, so anyway, theta. Okay, so this one can be W. What is this? Cosine. Adjacent hypotenuse. Okay, this is W cos theta. Then the one that actually causes this object to slide down the plane in that component, this force is the one that is responsible for that acceleration, will be W sine theta. Ooh, okay. So if they ask you what is the magnitude of force causing this to slide down, that's going to be W sine theta, because it is parallel to the slope. This is the force on the box. Any other forces we can add? Contact force, yes, correct. Okay, let's draw a contact force. Now the contact force we're going to look at is the force on the box itself. So I'm going to draw an arrow up there. This would be our N, normal contact force, and I draw it from the surface of the bottom. Because, you know, it acts on the surface only. And this normal contact force, by the way, if this box is not floating or sinking into the inclined plane, this should be the same as W cos theta. Most of the time, this will be the case if you're not being pressed. I mean, because one is pointing upwards, no, that way one is pointing downwards, right? So they have to cancel out in our Y direction, which is now tilted this way. So upwards force equals downwards force. Okay, we good. Any other forces? Now, normally, if the question says there's no friction, no other string, nothing, this is all. That's it, two forces. And these two will cause an acceleration down the slope, thanks to W sine theta. But wait, if you want to make this more complicated, we can add a string, like what we saw just now. So maybe I just want to add a tension force. And ta-da, this is a force. So I say, okay lah, this is tension, or it could be any force. Depends on the question. Check the question. Is there an external force, an engine force, or what? Tension force. Anyway, I'm just going to draw that. So this force is in the direction of the horizontal component, which is now our tilted axis. Oh man, this is tilted. So this tension force will be the one fighting against this W sine theta, because one is pointing uphill, one is pointing downhill, or positive X, negative X. Great. What are we missing? The final one, friction force. Which direction should we point? Great question. It really depends. If I want to know if there's friction or not, I need to know three things. Is this block moving or not? If not moving, this is it. Stationary equilibrium. So I'm going to say if equilibrium. Ooh, what the equilibrium means. Oh, never mind. We'll get to that first. If the block is not moving, no friction at all. No need to draw. If they say the surface is smooth, no friction. That's it. But if they say there's friction and you know which direction the block is moving, you have to draw friction. So let's assume that friction is going to move. No. Let's assume that the block is sliding downhill with some velocity or acceleration. Is moving downhill. Maybe the tension force is not enough to counter this. Okay, sure. That means your friction force will oppose that and point upwards. Let's give a small F down there. Alright, force. Okay, and that is going to be opposite to the direction of motion. There are no wheels or walking things here. This is just an object being dragged through a rough surface. But what if you have an object that is going uphill? I'm going to copy paste it here in the side so I don't have to redraw everything. Alright, I've done my copy pasting. So motion downwards, if the block is moving down, you got friction opposing that thing. If you have the block actually moving upwards because tension is powerful enough to pull the block upwards to overcome weight and actually pull the block up the hill, then you have to draw friction in the opposite direction. So I'm going to draw this little F arrow here, and that is if the surface is rough, but it's still in opposite direction. And this will generally be what you encounter the most. Okay, So really, it depends. You need to see the situation, you read the question carefully. The only way to figure out whether you understand this or not is to try out some past year questions. And a reminder, if they ever ask you to find acceleration on an inclined plane, step 1, draw all the forces. Step 2, remember your Newton's second law. Do you remember Newton's second law? Please say you remember Newton's second law. We have Newton's second law, which is the net force acting on the object equals to mass times acceleration. That's why we learn Newton's second law, because now there is so many forces that contribute to the net force. For example, if I say in the horizontal direction, okay, so net force in the horizontal cause acceleration in the horizontal. You see, I add an X there, right? That will be separate from vertical acceleration. So net force in the vertical equals to mass times acceleration in the vertical. Remember, horizontal vertical is tilted. We tilt our axis, okay? So by horizontal, I mean slanted or rough, slanted on the plane. So if you look at any diagram, let's say this one, to make it simplified a little bit, what is the force that is contributing to the net force? You have to look and you say, oh, in the horizontal, there is tension here, there is force, there is W. Oh, okay, so we list it out. Tension is upwards. So there's tension, there is, what else? Who else is pointing upwards? Nobody else, right? I don't know. So tension, there is the horizontal component of weight, and there is friction. In this particular case, if we say anything upwards is positive, then tension is positive. Friction is negative. Weight downwards is negative, because they're pointing opposite direction. Some uphill, some downhill. You need to know the signs. But all in all, these are the 3 friends that will contribute to the net force. In the horizontal, why I draw down there? I say, this is horizontal Fx. Okay, never mind, we change up there to y. So in the y, by vertical, we mean perpendicular to the plane. So that will be 2 forces only, very lonely. The first one is normal contact force, upwards. So if we say upwards is positive, then sure, positive. Then whoever is downwards exactly opposite, that will be negative. So there is weight, 1 up, 1 down in the tilted y-axis. So we have N and we have the vertical component of weight. These 2 contribute to the net force. You add them together for Fy. And then you can find the vertical acceleration, if any. Okay? So apply your dynamics, know the forces, draw the forces. That's all for this video. I will see you in the next one.